Good afternoon, Edward. Welcome. We're looking at, we're going to finish up, that was Jessica, by the way. We're going to finish up 8.5 today, starting with questions on homework 8.5. Do you have any questions on the homework that was due today? Ethan.
For the number 24, when you have a trigonometric function, how do you deal with like making like a sub n? Like how do you?
Right, so here we have a trigonometric function of multiples of pi, and so I just wrote out a few terms. With n equals 1, we got cosine pi, n equals 2 is cosine 2 pi. So since cosine of pi is -1, cosine 2 pi is +1, that cosine of n pi is just an alternate representation of the alternating factor, which is ordinarily seen as either -1 to the n or -1 to the n plus 1. It's just a fancy way to do it. -1 to the n. In this case, when n equals 1, it comes out negative. So yeah, as far as cosine of n pi goes, it is always equal to the -1 to the n. So for all natural numbers n. Further questions on the homework that was due today? Yes, Jessica.
21.
All right, let's take a look at number 21. Now this one is another situation where we're alternating in an unusual way. Sine of an odd multiple of pi over 2 is just -1 plus, so sine of pi over 2 is 1, sine of 3 pi over 2 is -1, it's going back and forth. Guido Ubaldus used this series to prove the existence of God. He tried to prove that 1 is equal to 0 using this series. To just show you a little bit of what Guido Ubaldus did, what was his reasoning, see if you can spot the mistake. It turns out that God actually does exist, but Guido's proof does not establish it. Guido Ubaldus said that 0 is equal to 0 plus 0 plus 0 plus 0 plus ... forever. And then he said that 0 is equal to 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus ... forever. So far, his logic is impeccable. Next, Guido said 0 is equal to 1 plus -1 plus 1 plus -1 plus 1 plus ... forever. Now, since -1 plus 1 is equal to 0, he wrote 0 as 1 plus 0 plus 0 plus ... forever, which means that 0 is equal to 1. His reasoning was that God exists because this math proof shows that something can come from nothing. 1 can come from 0. So, where is Guido's logic flawed? I mean, it is true that 0 plus 0 plus ... forever is 0. So we've got 1 plus a whole bunch of zeros. So this 0 came down here. Maybe for some of you, it might help if I put this right there. 0 is equal to 1 plus, I'll show a little bit more work. All 0 plus 0 plus 0 plus ... forever is 0. Where did Guido make his mistake?
You don't need parentheses.
Yes, there's many that would argue that he made the mistake in this line. It's like he's showing 1 plus, now he's grouping these together. The associative property enables you to do that. However, he included this 1, but not that -1. So because, like on this line, there's 1, 2, 3, 4, 5, 6 ones shown. Here there's 1, 2, 3, 4, only 5 ones shown. And so just the way that he paired it up was sneaky. It's deceptive. So Guido Ubaldus has a long history with series like this, but that's essentially what's going on here. Here we have 0 plus 0 plus ... going on forever. It's basically, but you can prove using the alternating series test that -1 to the n plus 1 converges. The nth term, a sub 1 is equal, or a sub n is equal to 1. It's just the invisible 1 here. it is true that 1 is a non-increasing function, it's greater than 0. However, its limit as n approaches infinity is not 0. So the alternating series test fails. We go to the nth term test, and the limit as n approaches infinity of a sub n is alternating back and forth, 1, -1, 1, -1. The answer is not 0, the answer is does not exist. Nor is the answer 1. According to Guido, 0 is equal to 1. And if you get 1, then you could say that it diverges. But the truth is, the alternating series 1 minus 1 plus 1 minus 1, etc., does have a limit that does not exist, therefore the series diverges. So that's an overview of what's happening in this proof. But there's a question. So let's try to have a solution sheet centered discussion. Jessica, do you have a specific question on this solution?
No, not right now.
If you are able to generate a solution sheet centered question, like how did you get from the first line to the second line or something like that, then I'd be happy to field it. In the meantime, we need to, so maybe as you're working on that, were there any other questions on the homework that's due today? All right, we're gonna jump in where we left off and take out your 8.5 handout, turn to page 1. While we're on page 1, I want to fill in the last 2 tests here. Let's fill in the details for the ratio test and the root test. Now, of all the tests in this unit, I'd say the ratio test is the most important. It could be it's the one that you will use most often, and certainly it links into finding intervals and convergence. And as we continue our work in calculus, when we come back to tests for convergence, the ratio test is the one that we will come back to most often. So to qualify for a ratio test, the series just needs to be a function of n. And there is only one step that we need to look at. There's one condition that has to be met for convergence. If the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, basically it's a ratio of adjacent terms, and if that limit is defined, L means it's a real number that happens to be less than 1. If you get an actual number that's less than 1, then the series converges if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than, rather is greater than 1, can't be infinity, but if it's equal to some limit L that's greater than 1, or if that limit does not exist, DNE does not exist, then the series diverges. By the way, if the limit L equals 1, then there is no conclusion from the ratio test. And then finally, the root test. If the limit as n approaches infinity of the nth root of the absolute value of, actually you don't even need the absolute value because we're going to talk about absolute convergence today. So the nth root of a sub n, if that is a value that is less than 1, then the series converges. And if the limit as n approaches infinity of the nth root of a sub n is greater than 1, then the series diverges. Now, the root test, honestly, we just don't use it very often. There's a few questions on the homework that's due on Friday where you have to use the root test, but the ratio test is far more valuable than the root test. Question? Yeah, you know what? I think I do have an extra note packet for you. And where did it go? Oh, here it is. Okay. The note packets. All right. Now, as far as filling in other things that we skipped over, yeah, this table, if you weren't here, then this is huge because I'm actually going to give a portion of the test, it's just one page. It's a 5-page test. I'm going to give you page 5 on Friday. I'll give you like 15, 20 minutes on Friday this week. Pages 1 through 4 will be Monday. So that way, the part on Monday won't be so time pressured. It's not that unusual that on a review day, I might give you a little bit of the test, but I'll even give you a hint. There's going to be a diagram like this on Friday's part of the test, where you're going to have to show that you understand your vocabulary. And there's so many of these vocabulary terms that mean the same thing. Actually, we can circle a fourth one right here. 3, 4, 6, and 7 are all synonymous. The first term of the remainder is called the first throwaway term. It's also called the maximum error, which means it's an upper bound on the error. The first throwaway term is an upper bound on the error. In fact, number 7, upper bound on the error, that's the main thing I want you to visualize. We kept the first term, the second term brought us down to 0.5, plus a third brings us up to S3, minus a fourth brings us down to S4, plus 1/5 brings us up to S5. We decided that we're going to use the fifth partial sum as an approximation of the alternating harmonic series. Now, the first term that we throw away is 1/6. It goes minus 1/6. And so visualizing the relationship between the length of the orange segment, segment IJ, and the length of the black segment, segment KL, is a visual reminder that the first throwaway term has an absolute value that's greater than the error. The first throwaway term is an upper bound on, or bigger than the error. The error is simply the difference between the approximation, S5, and the truth, S. So the error is segment KL. So it's very important, as long as you see in this diagram, that the first throwaway term, also known as the first term of the remainder, is an upper bound on the error, that the orange is a little bit bigger than red, also known as the maximum error, then you're in good shape. Now, one thing we skipped was number 8, the sign on the 40th and 41st terms. So the sign on the 40th and 41st terms can be understood by looking carefully at the alternating factor. When n is 40, the exponent is 41, and -1 to an odd number is negative. So the 40th term is going to be negative, and the 41st term, by the same logic, is going to be positive. Therefore, we're going to be able to write inequalities, and one of these is true. See if you can figure out which one is true. Is the 40th partial sum less than the truth, less than the 41st partial sum? Would that be the case? Or would it be the case that the 41st partial sum is less than the truth, S, is less than the 40th partial sum? Being able to write inequalities like this is important, but it's not obvious, because sometimes the 40th partial sum will be an underestimate. Sometimes the 40th partial sum will be a high estimate. It'll be an upper estimate, depending on what the last term was. Well, keep in mind that the 40th partial sum, since the 40th term is negative, it is an underestimate. It's a low estimate, because look, first partial sum is bigger than S. Second partial sum is less than S. Third is above, fourth is below. So it just keeps alternating back and forth. The pattern is that, in this case, the pattern is that the odd subscripted partial sums happen to be larger than S. The even subscripted partial sums tend to be low estimates of S. So that would have been changed had this been like n plus 2 instead of n, or n just plain n. You have to actually look what that is. So since the 40th term, we already said that the 40th term is negative. So when you added on that 40th term, it brought the approximation down a little bit less than S, and then the 41st is greater than, so it turns out that this is the case, but it's not true because 40 is less than 41. It's true because the 40th partial sum ended with a negative term, and so that brought it down below the truth. That would have been changed had I made this alternating factor n plus 2 or n plus 3. So that's what's going on there, and I think that wraps up what we were going for on page 2. Let's go to page 3. Does the series converge or diverge? And as far as these being interesting, keep in mind that number 1 is the alternating harmonic series in disguise. Put a 1 in front, it's -1, so you could rewrite it, thinking of the discussion that Ethan and I had a few minutes ago. You could rewrite this problem as something a little more familiar. -1 to the, it's going to be either n or n plus 1 times 1 over n. Well, which one is it? Let's check. When n equals 1, we got cosine of 1 pi. What is the cosine of pi, class? What? -1. And -1 to the 1 is also -1, so this is correct. If it had been out of sync, I would have had to make that n into an n plus 1 or something. And try again to change everything to blue so that it shows up better, something better about blue. Okay, so yes, you're saying alternating, it's the alternating harmonic series. Now that you've proved the alternating harmonic series converges, from here on out, you don't even have to run the test because it's known to converge. You can say the alternating, actually, you can just say this is the convergent alternating harmonic series. That's all I have to say. So harmonic series, you don't really have to test. I mean, it's a P series. Since these series are so famous, so well known, you can just say this is the convergent alternating harmonic series. All right, so here's another way of writing -1 to the n. By the way, it is, according to the alternating series test, can you foresee, as you go through the 3 steps, can you foresee what's going to happen if we were to apply the alternating harmonic series to this? Just run through it in your head. Do you got a conclusion or no conclusion? Right, I should say converges or no conclusion. You'll define a sub n just as this piece. This is basically -1 to the n. It's 1 pi over 2, yeah, so it goes positive, negative, positive, negative. So this is just a fancy way of writing -1 to the n plus 1, not -1 to the n. This is -1 to the n plus 1 because it starts with positive 1. Okay, so a sub n is going to be defined as this. Is it positive? Is it greater than 0? Yes. Is it non-increasing? Yes. Is the limit equal to 0? No, the limit's not equal to 0. So this is a situation where you would say, okay, alternating series test didn't give us a conclusion, so then we would go to the nth term test. And in the nth term test, which in terms of the documentation, really what you would write is just nth term. And you would define a sub n as the entire thing, which is really -1 to the n plus 1, n cubed over n cubed plus 6. And your one and only step would be to take the limit as n approaches infinity of a sub n, which would give you basically plus, it's going to +1, -1, +1, -1. So that limit does not exist. That's good enough to say, therefore, series a sub n diverges according to the nth term test. This next one, if you were to go to, yeah, this is natural log n. If it's a horse race between natural log n and n, which goes to infinity faster, natural log n or n? Class. Yeah, n goes faster. So, I mean, you could do L'Hopital's rule on this when you're taking the limit. But in the alternating series test, be aware that sometimes, we don't have to write the word test, underlining it means test. So, occasionally you're going to have to use L'Hopital's rule when you're evaluating these limits. So you would define a sub n as natural log n over n. Step 1, a sub n is positive, 2, a sub n is non-increasing. And step 3, when you take the limit as n approaches infinity of a sub n, that's the limit as n approaches infinity of natural log n over n, the form of which is a limit infinity over infinity. So L'Hopital's rule does apply to this. So according to L'Hopital's rule, we take the derivative of both the numerator and the denominator to get the limit as n approaches infinity. According to LHR, derivative natural log n is 1 over n. The derivative of n with respect to n is 1. So this limit is now 0, and that's a check then. So we checked all three. Therefore, series -1 to the n a sub n converges according to the alternating series test. All right, so those are a few more examples of using the alternating series test. Are there any questions on those three? Now, the concept of strictly alternating. To be an alternating series, the series has to strictly alternate. It goes positive, negative, positive. It can't go positive, positive, negative, 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 positive, negative. It can't just alternate in a willy-nilly fashion. It has to be strictly alternating. And sine n over n cubed is not strictly alternating. Think about it. Sine of 1, that's 1 radian. 1 radian is about 57.3 degrees. Sine of 1 is positive. Sine of 2 is positive. Sine of 3 is also positive. It's not until you hit n equals 4 that sine n goes negative. 4, 5, and 6 are negative, so it's not strictly alternating. It goes positive, 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 negative, negative, negative. Not, it's not perfect like that, but we're going to take a look at how we could use the direct comparison test. Direct. Okay, so according to direct comparison, it is helpful to see every now and then that, well, I'm going to say a sub n is sine n over n cubed. This is actually a great series for direct comparison because sine n, if you know the range of the sine function, it's always less than or equal to 1. Have you noticed that sine oscillates between -1 and +1? So sine n is always less than or equal to 1. So let's pull out of thin air a definition of b sub n equals 1 over n cubed, which is wonderful because that's a convergent p series. So step 1 is, this is a problem. Look at this, 0 is less than or equal to a sub n is less than or equal to b sub n. Can we affirm that? Is a sub n always sandwiched between 0 and b sub n? Class? No, it is not. Because sine n, a sub n sometimes goes negative. So, we need a new concept. It's called absolute convergence and conditional convergence. So, this used to be just a teaching tool, but a couple of years ago, College Board decided to put absolute convergence, conditional convergence on the AP test for Calc BC. So now this is the real deal, and they expect you to learn this. It's a really convenient concept, especially in a situation like this, when you're just off by, sometimes it goes less than 0. So if series absolute value a sub n converges, then series a sub n is absolutely convergent. What's going on here? A series that converges even when you rob it of its negative signs. Like, let's take a series. I'm just going to pull up some paper here that I can look at. So let's take the alternating harmonic series. 1 minus a half, plus a third, minus a fourth, plus a fifth, minus plus dot 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 forever. that is our series A sub n. It's the alternating harmonic series. What is series absolute value A sub n? What if I were to take the absolute value of every term in the series? Would that change its divergence or convergence status? Well, let's see. What does the alternating harmonic series do? Remind me, does it converge or diverge? The alternating harmonic series converges to about 0.69. It's actually the natural log of 2, right? So it converges to about 0.69. We saw that yesterday. Now, what would happen if I were to take the absolute value of every term, or in other words, if I said, hey, alternating harmonic series, you can't have your negative signs anymore. We're going to take them away. Let's see if you can still converge. Well, notice what happens if you steal the negative signs by taking the absolute value of every term. Does it still converge? No, now it's the harmonic series which diverges. You see, what the concept of absolute convergence means is, it actually makes a lot of sense. If you can get a series to converge even when you take away its negative signs, and it still converges, wow, this series is really bent on convergence. It's like, it is absolutely convergent. Now, if a series is absolutely convergent, then there's one thing we know for sure. It's convergent. This thing doesn't even need its negative signs and it's going to converge. That's how convergent it is. So if series A sub n is absolutely convergent, then series A sub n converges. So if you can show that a series is absolutely convergent, then one thing you know for sure, it's convergent. Okay, how about conditional convergence? Well, it turns out that the alternating harmonic series is a great example of a series that is conditionally convergent. It converges just fine on the condition that you let it keep its negative signs. Oh, you only converge if we let you keep your negative signs. Okay, well, you're convergent on the condition that no one steals them from you. So, if series absolute value A sub n diverges, so it's not absolutely convergent, and if series A sub n converges, so like if you take away its negative signs, it diverges, but if you let it keep its negative signs, it converges, then we say that series A sub n is conditionally convergent. Okay, so since the direct comparison test failed, because step 1, we could not affirm that A sub n was sandwiched between 0 and B sub n, we're going to switch gears and we're going to try to handle this series by, in fact, you know what, in case, so we'll say no right here, but no. Usually we check it off because yes, no, that didn't work. So now what we're going to do is our first example of showing that a series converges by showing that it's absolutely convergent. So it's more like an essay than it is a math problem, but you'll see that as you progress as a mathematician, the higher and higher math courses you take, the fewer numbers there are and the more words. Each math course gets more and more words, fewer and fewer numbers. Sorry, but that's what's going to happen. This is going to be mostly a paragraph. So here we go. How are we going to structure this? Well, whenever you're hoping to show that a series converges by arguing, well, it's absolutely convergent, therefore the series converges, here's how we structure it. First of all, you announce the question that you're asking. You say, is series A sub n, we have to define our A sub n, So let's just do that up front, as we've been doing with all the other ones. We're gonna say a sub n is sine n over n cubed. So let's get ready to write what amounts to an essay. Okay, so we write the question, is series a sub n absolutely convergent? Question mark. That's the same thing as asking, does series absolute value a sub n converge? Question mark. They're the same question. If series a sub n is absolutely convergent, then series absolute value a sub n converges. So let's pick a test. Let's do what we did before. Let's do the direct comparison test, but not on the original series, on the series where you take absolute values of every term. Okay, so here we go. Direct comparison. I'm going to let b sub n equal the absolute value of sine n over n cubed. Circle, I'm going to compare that to 1 over n cubed, which is my c sub n. Instead of a and b, I'm using b and c. I've got to go down the alphabet a little bit to get enough letters. Now, I think we can agree that this is a less than or equal to symbol that we put in the circle, because sine n is always, due to its range, less than or equal to 1. Okay, now let's go to step 1 of the direct comparison test. Now we can say that 0 is less than or equal to b sub n is less than or equal to c sub n. This time we can affirm that claim. We've taken care of the absolute value issue too. What do we know about c sub n? Can you tell me, can you anticipate for me what we're going to say in step 2? You've done this direct comparison test before. You can tell me what's going to be said. What happens in direct comparison? Scott, you want to give it a go?
Yeah, so the series of b sub n.
Actually, we're going to say, yeah, series c sub n.
Converges.
We have to say it's a convergent, a convergent what?
A convergent p series.
Yeah. Usually in direct comparison, step 2, we hope that step 2 will be talking about either a p series or a geometric series. Those are the two that we usually get. So we're going to say c sub n is a convergent p series. What is your parenthetical justification for that?
That would be p is greater than.
Well, first of all, tell me what p's value is.
P is equal to 3.
And into which category would you place 3?
Greater than or equal to 1.
It's just greater than 1. The equal to 1 in p series is, just remember, harmonic series is p equals 1. You know the harmonic series diverges. So the p equals 1 has got to go with the divergent half of the interval, or the divergent portion. So it's in the greater than 1 category. Therefore, series b sub n converges. Hopefully you're writing smaller than I am. But once you say series b sub n converges, you're not done. Because when you say, therefore, series b sub n converges, you have to finish the essay by saying, therefore, series absolute value a sub n converges. And it's a lot. There's 2 more. You say, therefore, series a sub n is absolutely convergent. And what do we know if a series is absolutely convergent? I mean, this series converges even though we stole its negative signs. So what do we know about the series? This is our final therefore. Moose, do you know? Check what we said on the other page about what we know when a series is absolutely convergent. Once you've established that a series is absolutely convergent, what do we know about the series? Do you have this statement about absolutely convergent there? Let's take a look at it. Should be on the previous page. See if we can find it. No, maybe it's on this page.
Series A sub n converges.
Moose, take a look at this. If a series is absolutely convergent, what do we know about it?
It's the series covered.
And the series converges. Now, hopefully, that's clear to you why that would be the case. I mean, it's kind of a nice way to prove convergence. It's like, this thing is absolutely convergent, which means it converges even when you take away its negative signs. So therefore, series A sub n converges. You have to follow this all the way through. Each link has to be there in the argument. We showed that series B sub n. Now remember, B sub n was the absolute value of A sub n. And if series absolute value A sub n converges, then it's absolutely convergent, therefore the series converges. Do you have any questions as to what the reasoning is on this one? So, ladies and gentlemen, are we all here? Is everyone? All right, so that's your first example. Now, sometimes what's going to happen is that you're going to go through to try to prove that a series is absolutely convergent, and it will fail. But then you'll say, oh, by the way, it does converge. The series converges. Therefore, the series is conditionally convergent. So every series is either absolutely convergent, conditionally convergent, or divergent. And there's 4 questions on the homework where you have to take a series and put it into one of those 4 categories. Now, I'll be honest with you. Run the nth term test in your head right away. If you're looking at a series and it diverges by the nth term test, then you're done. Don't mess with absolute convergence and conditional convergence, because that's a fast way to say, oh, I know which one it is. It's divergent. So keep that nth term test in your mind as you're going through. Okay, so that's that page. Wow, we finished up that page. And let's go now, let's see where we were on this. We're looking at, this is where we were. Okay, now, we did 2 of these 4 questions in class yesterday. We got a sigma notation approximation. So our sigma notation approximation, since we said T is 11, the first T for throwaway. So I know, Rapunzel, you missed a lot of this. We'll do some more examples so that you'll see what's going on. But the first throwaway, the subscript, see, it's not the first throwaway term. It's not the 11th term. It's the subscript of the first throwaway term. We don't throw away the 11th term. We throw away the term that has a subscript of 11. We don't always start at 1. This one started at 2. That's why we are so precise in defining T and K. T is not the first throwaway term. T is the subscript of the first throwaway term. K is the subscript of the last kept term. K is for kept, last kept. T is for throwaway, first throwaway. So that's a nuance that really matters. So we kept from 2 to 10, subtract and add 1, that was 9 terms. Now, that's why the answer to part 1 was the sigma notation is this guy right here. A decimal approximation. Now, out of curiosity, this is something that didn't come up on the homework. I thought for sure someone was going to ask this question. But how many of you honestly were wondering how many minutes it took me to do the 1,000 terms? What was it? How many terms? 1,000 terms. I typed in the home screen program. I pressed enter 1,000 times. And here's the home screen program. And 498, so by the time I got to 500, notice it was alternating between 0.692 and 0.694. The idea was to get an approximation that's accurate to the third decimal places. And even after 500 partial sums, they're two thousandths apart. So I kept going. 699, 7. By the time I got 700, there's still 0.69. Here's 0.6938, 0.6924. It wasn't until, and to be honest with you, I can go. My software is sensitive to enough that I can do it like that. So 20. I lost count. Okay. 1, 2, 8. 20. 40. 60. 80. 100. That's all it took for me to get to 100. So I was thinking, wow, that's way faster than what Jessica was doing the other day, because I think the handheld calculator is not nearly as responsive, but because the processor on my Mac is so fast, I was able to get up to 1,000 on my home screen program in under 5 minutes. It really didn't take long at all. And some of you might have been wondering, why did you do that? Why didn't you just use sum sequence? Well, it turns out that sum sequence was overwhelmed by the number 1,000. It couldn't do it. The calculator could not pull it off. Let's take out your calculator and find out why it is the home screen program is better than sum sequence. So on this particular homework, oh, by the way, how many of you pressed enter 1,000 times when you were doing the homework? How many of you thought, wait a second, how many of you thought, he expects me to type enter 1,000 times, I'm not going to do it? Is there anyone who's in that category? Okay, so some of you realized what was at stake. He said, and you were probably influenced by Jessica. It's like, Jessica, she took like 20 minutes just to get up to 400. I'm not going to waste that much of my life. So let's pull up the graphing calculator. And let's see, oh my goodness. We're actually making pretty good progress. You have to do an example of the ratio test and look at intervals of convergence using the ratio test. As long as we can get there, we're fine. But I just want to help us develop our calculator skills. So let's take a look at this problem from the homework. It was the alternating harmonic series, -1 to the n plus 1 over n, which we'll find out later is natural log 2. We'll find out why that's the case. So here's what some of you might have wanted to do instead. Instead of writing this as the summation from n equals 1, okay, so we can do this by going to sum sequence. Notice the list command on your calculator. A sequence is a list of terms, so it makes sense to go to the list submenu. And on the list submenu, on the list menu, go to the math submenu and pick up item 5, which is sum. A series is a sum of a sequence. So let's type in sum of a sequence. So second list, ops, sequence. There are 5 arguments in the syntax for sum sequence. The first argument is the function, which is parentheses, -1, close parentheses, caret, quantity, n plus 1, close quantity, divided by alpha n. That's a sub n. The first argument in the syntax is the function of n, a sub n. The second argument in the syntax is the variable that is being guided by the index of summation. The third argument in the syntax is the lower limit of summation. We're going from 1 to 1,000. And the fourth argument is the upper limit of summation, 1,000. And the fifth argument is the increment, but if you don't put in a fifth argument, it defaults to 1. So this is the summation. Basically, it's the 1,000th partial sum of the alternating harmonic series. Should be pretty close to natural log 2 when you press enter. I believe it overloads. Error invalid dimension. I would actually like to add this to the homework solutions to show people why you need home screen programs. That is an error. And let's just put this in to, yep. Yeah, so the home screen program is really pretty nice. But notice that if you just wanted the sum of the first two terms, if you just want to add it up from 1 to 2, that's 1 plus negative 1/2. It should give us an answer 1/2. Oh, it does very well for the first two terms. I wonder if it's capable of adding up the first three terms. Well, of course it is. Will it add up the first 100 terms? First 100, no problem. How about the first 500 terms of the alternating harmonic series? This kind of stuff is fun. You're just trying to find where it breaks down, why. By the way, when you compare this to natural log 2, they're pretty close. Natural log 2, they agree. Oh, look at this. After only 500 terms, it's accurate to within the 1,000th. Keep in mind that our method for finding the subscript of the first throwaway term is an overkill method, because the actual error is less than the maximum error is less than the allowed error, which means that the actual error is way less than the allowed error. So we didn't really need anywhere near 1,000 terms. But according to our overkill approach, 500 would have been enough. 500 terms would have gotten it. But our method will reliably find an upper bound on the number of terms that we need in order to approximate a series to within any boundary. So that's just a little bit of calculator stuff there, just to keep you conscious. How many of you are currently unconscious? Just, yeah, okay, just less than half. Zero is less than half. How many is it really? So. All right, so not even half? This is going to be stunning to Edward when he hears that statistic. Wait. Okay, so let's save that. Save it, and I want to, oh, the Guido-Ubaldus stuff is in here, I think. I don't know if I want that to be in there. The Guido-Ubaldus problem, I got it from Larson's 5th edition. I think it was Larson's 5th edition. But yeah, if you Google him and look him up on Wikipedia, you'll probably find out about how he thought that this was going to prove the existence of God. Print and export to PDF. Okay, so while the networks are on commercial break, we're just going to save this, and then we'll be back online momentarily. Okay, so back to the show. Welcome back. Okay, so you might be wondering, how did that happen? Why did we do that? Okay, so it's because you can type this into your calculator. Now we need the decimal approximation for part B, and for number 2. This decimal approximation thing right here is what actually prompted our detour into some sequence. Because there's going to come a day when you don't want to press enter as many times as are called for. You're going to want to get your decimal approximation not from a home screen program. You're going to want to use some sequence. So let's write down just write down the syntax. Sum parentheses sequence parentheses. And then another parentheses for -1, close parentheses, caret, open parentheses. No, we don't need parentheses there. That's just an n. So caret n divided by quantity n caret 3 minus 2. That ends the first argument in the syntax, comma n, comma 2, comma 10. Double right parentheses. Technically, although you will not get an error if you just type in one right parentheses. Technically, the first right parentheses closes off the sequence, and the second right parentheses closes off the sum. So you can get your 3 decimal approximation using either a home screen program or the sum sequence command on your calculator. Some of you probably even have your calculator set up so that you can do the sigma notation and all that stuff if you're in some sort of fancy math print mode. So, but whatever, you can use your calculator to get the 3 decimal approximation that way. Now, third, a 3-part sigma notation approximation. This is where our talk earlier today about which one do we use? Do we use S40 is less than S is less than S41? Or do we use S41 is less than S is less than S40, the 40th partial sum? So the 3-part sigma notation is where that comes in. Now, we're keeping 10. So the subscript of the last kept term is 10. Is our approximation, is it an underestimate or an overestimate? Tell your fellow group members, just actually the conscious, the unconscious ones, just let them rest. They're obviously very tired. But the ones who are awake, tell them, do you think that that this partial sum is less than S or greater than S? Go ahead and talk. Is it an overestimate or an underestimate? All right, who has a verdict on this, or at least an opinion that you'd be willing to defend publicly? Is our approximation, our decimal approximation, which by the way, came out to be, did we ever actually write it down?
It's natural log 2.
No, that's the exact value. Well, I want to know what's our approximation of natural log 2. Is our approximation less than natural log 2 or greater than natural log 2? That's the question. On your calculators, please type in the 3 decimal. You know what, let's write down what the 3 decimals are. Use some sequence to type this in now. I'm going to tour the room to see what you come up with. Show me on your calculator what you typed in for some sequence. Go ahead and press the buttons. Show me what you have. Go to your list menu, or you can do it there. It's go to list, or some sequence on list is really the way to go. Because then we're all doing the same thing. If everyone's using some sequence, then we're all on the same playing field. Max, did you have your calculator?
No, it's not.
Oh, we can't. Go ahead and bring your phone up.
Alright.
Bring your phone. I don't know what it is
I
about.
don't know if my I might have to.
No, don't thank you. Those are nice. I came out ahead on that one.
Fair.
All right. So hopefully everyone typed in some sequence of -1 to the n over n cubed minus 2, comma n, comma 2, comma 10. And those of you who did type it in, it probably looked something like this. Watch this. I'm going to pull it up again, and it's -1, and I can just edit this one because I've got -1 to the n. So watch this. I'm going to go in and delete a few items. Delete, delete, delete. Divided by insert the quantity, insert a gain, cubed minus 2, close quantity, we're going from 2 to 10. So when you did yours, did you get a 3 decimal approximation of 0.138? Raise your hand if you did. That's what you got? Okay, so that's pretty good. 0.138 is your 3 decimal approximation. And do we happen to know what this thing is? No, we don't. So 0.138. So, number 2, 0.138. Use a wavy equal to indicate that's an approximation. On the AP test, they will take off, on a 9-point problem, they'll take off a point if you write an equal sign instead of an approximately equal to symbol. So get your stuff together, okay?
Are you serious?
I'm serious. It's on the rubric. I'm not up here saying things that are not true. I'm saying it publicly in front of the whole room. It's true. They take off a point. So, next, Let's go to part C. I asked you a question, is 0.138 greater than the value of the series or less than? Raise your hand if you think it's greater than. You think it's an overestimate. Okay, hands on. Raise your hand if you think it's a low estimate, if it's lower than the truth. Here's how you find out. It goes above the truth, below the truth, above the truth, below the truth. So what did it do last? Put a 10 in for n. What -1 to the 10th is +1. So that means the very last term that got added on took it above the truth. So that's why this is a high estimate. Therefore, your 3-part sigma notation is, I've kind of run out of room here. So for part 3, I'm going to, 3 and 4, I'm going to say next page for the notes. You probably have room to write it down. But 10th was high, so that means that S10 is less than S is less than S11. But that's not sigma notation. Your 3-part sigma notation approximation for number 3, the answer is the summation from n equals 2 to 10 of -1 to the n over, is it n cubed minus 2? Is less than S, is less than, and then C. One of the upper limits of summation will be K, the other upper limit of summation will be T. It'll be either K on the left, T on the right, or T on the left, K on the right. So that's going to be the summation from n equals 2 to 11 of -1 to the n over n cubed minus 2. That is a 3-part sigma notation inequality, and this is HQ. This is a high quality approximation. What we had earlier for number 2, that was an LQ, a low quality approximation. When you just say S is wavy equals, get it together, 0.138. That's a low quality approximation. Low quality, because I don't know whether it's too high or too low. Now I have a high quality approximation because I'm seeing my 10th or my partial sum in the context of S. And then the 4th thing they asked you to do was number 4, a 3-part sigma decimal approximation, include home screen program. So 10, we did the home screen program. If only I pressed enter one more time, then I would have been able to see the other one. So sigma / decimal. So basically what's going on here is that for number 4, I'm going to say A is less than S is less than B, where A is approximately and B is approximately. So actually, I know what A is exactly. I don't have to say approximately there. So I'm going to say A equals the summation from n equals 2 to 10 of -1 to the n over n cubed minus 2, which, by the way, I'm going to get an approximation for that approximation. And B is the summation from n equals 2 to 11 of -1 to the n over n cubed minus 2, which is approximately what? So I already know that one of those is, hello, where did my calculator go? There it is. So I know that's 1. Go press second entry and edit the 10, make it into an 11. So we have a lower bound and an upper bound. So the truth is, I'm sorry, upper and lower. Okay? Yep, I had that mixed up. So A and B. So what we have to do here is switch the A and the B around, because we said that A was an, aha, I did that both times. So you're probably wondering whether or not you wanted to bring that to my attention. And so, but would you agree that 11 brings it low and 10 is the one that's high? So that means that A is here, B is there. So now we can say that based on this screen that I'm going to pull right in, based on the calculator work, I can say that the sum, it's not really the 11th partial sum because we started at n equals 2, but I am going to call this S sub 10. Even though it's only the 9th partial sum, I'm going to call it S sub 10 because I'm ending at 10. And we're going to call that approximately 0.138, and this is approximately 8.137. So sure enough, it makes sense that what I'm calling the 10th partial sum, or what I'm calling S sub 10, and what we're calling S sub 11 are such that S sub 10 and S sub 11 are lined up like this. So S sub 10 is less than S sub 11 is less than S sub 10. So that's number 4. I wanted to make sure that you got the 2 high quality results. Both of these are considered high quality, whether it's with decimals or sigma notation. Now, let's go on to the next page. And here we get more practice with this. Looking at the sum sequence notation here. Here on the TI 83, 84, used to be we had the TI 86, TI 89, depending on the calculator notation. But based on what you see here, you're asked to write out 2 3-part inequalities. Sigma is less than S is less than sigma, and decimal is, okay, let's just do decimal for both high quality and low quality expression approximating this. So what if you're doing a problem, T came out to 21 and K came out to 20? What would be your low quality approximation for S? S would have a wavy equal sign. So as you look at this calculator work, what would you say is the low quality result based on the calculator work displayed? Ethan.
S is approximately the series or the sum. Of the
No,
series.
low quality. Low quality is just a decimal. There's no, yeah. So what would it be in decimal form?
1669.
Yeah, it's just the 20th partial sum. Because they said on the bottom that K came out to 20. So that means you just type this into your calculator, you get 0.669. But a high quality result would be based on the fact that, okay, notice that the 20th partial sum, or the 21st partial sum, you would expect it to be a little bit higher. So it's actually 20 is low, 21 is high. So it would be based on S, 20 is less than S is less than, let's just double check, yeah, is less than S21. So you would put sigma notation for each of those. But basically, the 20th partial sum is the approximation. In decimal form, you could say 0.669 is less than S is less than 0.716. So whatever the truth is, it's between these 2 boundaries. That's higher quality because it tells us not just what the approximation is, but we're saying it's somewhere in here. It's always higher quality to give it an interval. Any questions on this page? Okay, I think there's more on this handout, or is that the last page of the handout? All right, so need to do ratio test. And I've got this next handout. It's not, I haven't put it online yet, but the back page is blank. I'd like all of you to come and grab the paper handout, and let's go to the blank side. Let's do an example of the ratio test. Okay. On the blank side of this handout, let's find out whether a series converges using the ratio test. Use the ratio test. The root test is just like the ratio test. I'll leave it for you to just follow the examples that are in the homework. But by far the most important test for convergence is the ratio test. I'm going to pull up the 8.6 handout, I think. Got it, 8.5. What if they want me to save this version? No, they don't. We're good. So, here we go. We're opening the 8.6 handout. And no, those are the solutions. So we're going to go desktop, handout lesson plans, unit 8. And 8.6, here it is. So you're looking at this handout, go to the blank side of it. And here we go, example 1. And just FYI, this is the test you're going to be using most often. This is kind of a big deal. We're going to use the ratio test to find out whether or not the series, here's problem 1 by the way, it's the summation from n equals 1 to infinity of 2 to the n times n over n plus 1 quantity squared. Okay, so here we go. In the ratio test, you have to define your a sub n, which in our case is 2 to the n times n over n plus 1 squared, and the n plus 1th term, one term beyond that. So replace every occurrence of n with n plus 1. We're talking 2 to the n plus 1 times the quantity n plus 1 over n plus 1 is n plus 2 quantity squared. Okay, there's only one step to the ratio test. Since you've probably already written that down, I'm going to select it, make it a little bit smaller so that we have enough room to roll from here. Okay, step 1. It's going to be a long one. We always start out with the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Working horizontally for now, even though on the homework solutions I work vertically. That's going to be the limit as n approaches infinity of the absolute value of the n plus 1 term. I know it says 2 to the n plus 1, but let's write it as 2 times 2 to the n. It'll help us understand what cancellations need to happen later on. That's over n plus 2 squared. Now, instead of dividing by a sub n, may I please have your permission to multiply by the reciprocal of a sub n instead? So instead of dividing, we're going to multiply by the reciprocal, which is n plus 1 quantity squared over 2 to the n times n. Now, let's cancel stuff. The 2 to the n's cancel. Here we have n plus 1 times n plus 1 squared. Yeah, so that's as far as that goes in terms of just canceling things. But look at the degree. Upstairs we have degree 3, and downstairs is degree 3. So the limit comes out to be the ratio of lead coefficients. And the categories for ratio tests are greater than 1 diverges, less than 1 converges, greater than 1, therefore series a sub n diverges. Any questions on our first of 3 examples for the ratio test? Okay, in our second example, by the way, ratio test is great when you have variable exponents, 2 to the n. Another thing that indicates that you might want to use the ratio test is factorials. So, number 2, suppose our series is the summation from n equals 1 to infinity of n to the n over n factorial. Let's use the ratio test to investigate the convergence or divergence of this series. And, by the way, when the ratio test comes out to be equal to 1, that's no conclusion. You have to find something else to do. So, ratio test, here we go. Don't write the word test, just ratio underlined. A sub n is going to be n to the n over n factorial. How should I define a sub n plus 1 in this particular case? Help me out with this, please, Kennedy.
The quantity n plus 1 to the quantity n plus 1 over n plus 1 plus parentheses factorial.
N plus 1 quantity factorial, that's right. Okay, here we go. Step 1 is the limit as n approaches infinity of the absolute value of the ratio a sub n plus 1 over a sub n. That's why they call it the ratio test. We take the ratio of the n plus 1th term and the nth term. And if that ratio comes out less than 1, then it's going to converge. If it comes out greater than 1, then hey, that thing's diverging. This becomes the limit as n approaches infinity of, I'm going to put this on the next line because I need more room to write. So trying that again, it's going to be the limit as n approaches infinity of a sub n plus 1. Okay, yeah, we can write that. I'm going to write it a little bit different. instead of n plus 1 factorial, I'm gonna write it as n plus 1 times n factorial. That's the same thing, right? Because n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, all the way down to 1. So we're gonna break that up. Instead of dividing by a sub n, I'm gonna multiply by the reciprocal of a sub n, which is n factorial over n to the n. Okay, things cancel. So it appears that some of the things that cancel, the n factorials cancel. Now, we've got n plus 1 to the n plus 1, and there's an n plus 1 down here. Do you see how that cancellation is going to show up?
Yeah.
It's basically one of the n plus 1s is going to go away when you cancel. So I think it's fair to say that this n plus 1 is going to wipe out that plus 1 up there. So it's basically n plus 1 to the n over n to the n. That's a limit that's really quite manageable. Technically, though, it is, technically, that is a limit that you would use natural logs to evaluate. So limit as n approaches infinity. Absolute value is not going to do anything here because it's all positive. It's going to be n plus 1 over n to the nth power. So this is one that on L'Hopital's rule day, we learned how to evaluate these. This is in the form 1 to the infinity. The form of the limit is 1 to the infinity, and that's an indeterminate form. And we can get L'Hopital's rule to apply to it if we rearrange things a little bit. So I'm going to let y equal this limit as n approaches infinity of n plus 1 over n to the nth power and take the natural log of both sides. That's going to bring the n down front. So it's going to be the limit as n approaches infinity of n times the natural log of n plus 1 over n. So as n goes to infinity here, what's going on? We've got natural log of, this is going to be natural log of 1. The natural log of 1 is equal to 0. So it's 0 times infinity, which is also an indeterminate form. So if you rewrite this as the limit as n approaches infinity of natural log of n plus 1 over n over 1 over n, instead of multiplying by n, I'm going to divide by n-nth. Now I've got 0 over 0. That's an indeterminate form to which L'Hopital's rule actually applies. So according to L'Hopital's rule, I have to take the derivative of each one of these. Now the derivative of natural log blob is 1 over that, which is basically n over n plus 1, times the derivative of the blob, which is low d high, n minus high d low, n squared below over n squared. So that's essentially, let me just double check. Low d high is n, minus high d low is a quantity n plus 1. Draw the line square below. Wow, we really, that's 0. It's 0. No, n minus, and it's negative 1 over n squared. So it's minus 1 over n squared. But the derivative of the denominator is negative 1 over n squared also. So the negative 1 over n squareds cancel. You've got 1. So this natural log y comes out to be 1. We're solving for y. If natural log y is 1, then y is equal to e. So the limit comes out to e, which is in the greater than 1 category. Therefore, the series diverges. Sigma a sub n diverges. So, wow, it's been a long time since we've done a limit that was that difficult. Haven't used logs. And then finally, our last example with the ratio test has even more factorials. Let's look at the next one, which is the summation from n equals 1 to infinity of n factorial quantity squared over 3n quantity factorial. Factorials are a dead giveaway that you're going to want to use the ratio test. So ratio a sub n is going to be defined as n factorial times n factorial. That's what we mean by n factorial squared over 3n quantity factorial. A sub n plus 1 is a quantity n plus 1 factorial times quantity n plus 1 factorial over 3 times quantity n plus 1 is 3n plus 3 factorial. So let's take the limit, step 1, as n approaches infinity of the ratio, a sub n plus 1 over a sub n. That's the limit as n approaches infinity of. So, gotta be careful. It's n plus 1 factorial. With your permission, I'm just gonna write that as n plus 1 times n factorial. This other n plus 1 factorial is rewritten as n plus 1 times n factorial. And to be honest with you, 3n plus 3 factorial is the same thing as 3n plus 3 times 3n plus 2 times 3n plus 1 times quantity 3n factorial. You see where this is going? Instead of dividing by a sub n, I'm going to multiply by the reciprocal 3n quantity factorial over n factorial, n factorial. Lots of things cancel. Cancellations galore. N factorial is gone. The other n factorial is gone. The 3n quantity factorials are gone. All we're left with is degree 2 over degree 3. This limit is 0, which is less than 1. Therefore, the series converges. Now, our last example for the day is to show how to use the ratio test to find an interval of convergence. So turn in your handout back to, I believe it's this second page, page 2. It says, find the interval of convergence. And in the past, when we found the interval of convergence, it was a geometric series. And so finding the interval of convergence amounted to solving the equation absolute value of r is less than 1. But this is not a geometric series. So whenever the series of which you're trying to find the interval of convergence is not a geometric series, you use the ratio test not to find out whether it converges, but to find out for what values of x will the ratio be less than 1. So we're still going to have to define a sub n as x to the n over n. We're going to have to define a sub n plus 1 as x to the n plus 1 over n plus 1. But this time, since we want it to converge, we take our limit as n approaches infinity of a sub n plus 1 over a sub n, and we decide ahead of time we want it to be less than 1. We want to find all the values of x that make this limit less than 1. So, here we go. Solve the equation limit as n approaches infinity of x to the n plus 1 over n plus 1. Instead of dividing by a sub n, I'm going to multiply by its reciprocal, which is n over x to the n. I probably should have rewritten x to the n plus 1 as x times x to the n. So, limit as n approaches infinity. But those do cancel, leaving you with x and upstairs and n plus 1. We're taking not as x approaches infinity, but as n approaches infinity. And as n approaches infinity, all we get is the absolute value of x. So when the absolute value of x is less than 1, we can break that up into a 3-part inequality such that negative 1 is less than x is less than 1. But you're not done, because you have to test for convergence at the endpoints. It's called check the endpoints, which means you have to do 2 mini searches for convergence or divergence. First at x equals negative 1, first at x, and then at x equals positive 1. You'll see it in the homework solutions. But basically what you're going to have to do is say, when x equals negative 1, you know what the series is? It's the summation from n equals 1 to infinity of negative 1 to the n over n. Where have you seen that before? What is it? It's the convergent alternating harmonic series. So this one is it converges at that endpoint. Don't go away. At x equals 1, it's n equals 1 to infinity of 1 to the n, which is just 1 over n. Oh my goodness. That's the divergent harmonic series. Therefore, the interval of convergence is square bracket negative 1 comma 1 parentheses. It's all the x's that are from -1 inclusive to 1 exclusive. That concludes Unit 8. We are going to finish this handout on, so the answer is x
To the following
equals
students,
these
please come
numbers.
to Student Services, Vivian Singh, Nick Lee, Alice Dontra. Thank you.
All right, we'll see you Friday.